are going to talk about physical computing. Right now we did programming in the previous lesson. So in the next unit, we are going to now see how this programming we can do. How we can go to the next level. That means we can, do the physical things. In this lesson, you will learn about this microbit unit. Then before that, first we have to learn the logic in this, circuits in the programs. Okay. So in physical computing, uh, so we are going to learn there are basic three logic gates, right? When we are talking about physical computing, now there are three basic logic gates. Okay, that is the AND gate, OR gate, and NOT gate. Okay, right now we will describe one by one. Okay, please switch off your mics and listen. Huh? Please switch off your mics and listen. Okay, right. Now first we will go to the AND gate, right? Okay, now to explain the AND gate, I'm going to use this example. Now look at this, uh, water supply to this tank, right? Now look at this picture. Now here's the water supply to this tank. Now, so here there are two valves, right? Here I have named, they have named it A valve and the B valve. Okay, now in order to the tank to be filled, right? In order to this tank to be filled, we need to open this valve. And also, we need to open this valve too. Okay? Otherwise, if we open this valve and if we have closed this valve, will the water go into this tank? No. Okay?
No.
And yes, and if we open this valve if you open this valve and close this valve, we can't fill the tank. So in order to get this tank filled, we need to open both these valves, right? That is the analogy of the AND gate. So in the AND gate, if this now we will take A valve closed, and now I'm going to just describe what I described here in a table, right? So if the A valve is closed and also the B valve is closed, the tank does not receive water. Okay. So if both of these valves are closed, it doesn't receive water, right? And either any one of these valves are closed, it doesn't receive water. So here, if any one of the valves are closed, here it is closed and here it is closed. So they does not receive water. In order to supply water to the tank, we need to open both the valves. That is the logic behind AND gate, right? So in AND gate, if we take the open state as 1 and the closed state as 0, both valves should be open. So it needs to be 1 and 1 to get the output 1. Okay, so in order to fill the tank, we need to open both the valves. So if we get the open state as 1, we need both 1 and 1 to get the output 1. If either of these values are 0, we get the value 0. So similarly, in the AND gate, okay, now this is the standard symbol for the AND gate, right? We draw AND gate like this. You have to remember that, right? So if we consider these two inputs, just like the valves, right? So to get the output 1, these two inputs need to be 1. Otherwise, the output will be 0. Okay. If you input any 0 here, the output will be 0 in the AND gate. if you want to get one, these two inputs, sorry, these two inputs should be 1. That is the logic behind the AND gate. That means you have to have 2 ones if you want to get a output of 1. Right? Now, in these logic gates, in this AND gate, we denote 1 as the electric signal is present. Okay? When the electric signal is present, we denote it as 1. Okay? And if the electric signal is not there, we call it 0. Right? So if the state is, the electric signal is present, we show it by 1 in logic gates, okay, in this AND gate. So if that there is no electric signal, it is denoted by 0, okay, right. So I will show you one example, one more example, like this. If we consider, now just consider, this circuit, okay, this circuit. Now you have a circuit here. Now you have a bulb here, right? Now you have a bulb here. And you have 2 switches here, okay? 2 switches here, okay? Then we get this, I think here you have the battery. We say there are 2 batteries, okay? Right, so now you get the, now we should, right, so when you, if you want to get this bulb, lighted, if you want to get it lit, what should you do? You should switch on. If you switch on the one switch, will it, could you light it up? Only
No,
one
no,
switch? No. So
no,
you have to
no, madam.
switch, yes, both the switches, okay, to light it on. So this, this concept is there in the AND gate. So if you want, so here if you take electric signal as 1, so this should be 1 and this should be 1 to get this lighted, okay, this bulb. That means you have to close this and close this. These 2 switches must be on if you want to get this lighted, okay, otherwise we can't. With only one switch we can't. This is like the AND gate, okay, right. So I hope you understood. Now when we do some examples, you will understand. Okay, right. So when A and B are the inputs, we denote the output by A dot B, right? A dot B is the output. Okay, now this is the truth table. We draw a table like this. We call it a truth table. Okay, so we have input A and B. So the state, we have both no signals, okay, no electric signals, that means 0, 0. Then output is also 0. Then we have A0 and B1, only one is on, but the output is 0 again. And A is on, but B is the signal, electric signal is unavailable. So again, it's 0. If you want it to be 1, so both inputs should be 1. Okay. So it is denoted by A dot B. The output is A dot B. Okay. Right. Then we will go to the next gate. Then we have another gate. This is the O gate. Okay. Here in this O gate, so we have a valve here. Okay. Now this is the main water supply. We have a valve here and a valve there. Okay. So now if you look at this water supply, now if I close this valve, will this tank get water? If I close this valve, will it get water? I have
Yes.
opened this one. Yes, because this is open, right? Here, this valve is open and this is closed. But because this is open, it can get water from here. Now I'm going to close this valve and open this valve. Then will this water tank get filled? Yes. Yes, because I have opened this one here. The water can go from here, right? Now, for this instance, we can, the analogy of OR gate can be defined through this example. That means if one valve is open, the tank gets filled. If both the valves are open, again the tank gets filled. If we don't want to fill the tank, what we have to do is we have to close these both valves. So only if you want to close all the valves, only then this is not filling, right? It doesn't get filled when both the valves are closed. Okay, that is the only state that if we take 0 over here and 0 over here, then the output will be 0. Okay, right. So if we look, put it into a, table. Now, if the both valves are closed, that is the instance that we don't receive water. Only that instance, or both the valves should be closed, right? Then either one of these valves are open, it receives water. Here, open here and open here. And both the valves are open, it receives water, right? In order to not receive water, we need to close both the valves. This is the theory behind the OR gate, right? So if we take 0 for open as 0 for close and 1 for open. Now both the valves are closed here, 0, 0. Then the water supply is not there. Okay, so it is 0. And one valve is open, right? So it gets water. Here also one valve is open, so it gets water. And both the valves are open, it gets water. Now the same theory is applicable for OR gate. Now this is the symbol of OR gate, right? Now if you input two inputs like this A, B, then your output is A plus B. Now can you remember the output of the AND gate? It was A, what is it? What was the output of the AND gate?
A point B.
Yeah, A dot B, very good. The output of the AND gate is A dot B. Now the output of the OR gate is A plus B. Okay, A plus B. It doesn't mean that you have to add these two. It's just a symbol, right?
Excuse me.
A plus B. Okay, yes,
Excuse me, madam.
yes.
Madam, could A and B be swapped around? So could it be B point A and
Yes,
B
yes,
plus
yes.
A?
That's possible, yes. You can swap them, okay? A plus B or B plus A. Both are correct. Okay. So they are just symbols. These are just symbols. Okay. Right. Then if we take it to if we put it to a truth table, this is the truth table of the OR gate. So when both electric signals are not present, you get a 0 output. Now you can't light the, bulb. Okay. So if you take an example of a bulb, you can't light it if uh, there are no signals, electric signals. Okay. Then, electricity. If you don't receive any electricity, you can't switch on the bulb. So if we take no electric signals, so here it becomes 0. So if you have one anywhere, right? One, that means you have an electric signal here, right? So you get the answer output 1. Okay, output is 1. So if you draw, this, how can you draw this one? How can you draw it? How can you draw this one? So your yes. So this is our bulb. Okay. So you have a switch here. Okay. And a switch there. Okay. And the battery. This is like the O gate. Huh? One of these switches are on, right? If one of these switches are on, you get this bulb lighted, right? Is it correct? Yes. Is it correct? If one of
Yes,
these switches are on, you can light
it
this
may.
bulb.
And
Okay.
madam, the first switch has to the first switch has to move to the other terminal of the battery.
You mean which one? This one?
Top one. Top
This one, no? Here. You mean
no,
here?
the uh, top switch has to move.
Wait. I'll show you this. Huh? I will show you. Um, just wait. Okay, I will show you this one. This is it. Yes, I have. Yes. Now this one. This one. Okay, can you see this picture? It should be like this. Okay. It should be like this. Okay. Can you see this picture? That means if either one of the switches are on, yes, so it should be like that. Okay, this is not the correct one. Just I will draw it again. So if you have this here, you have to have these switches like this. Okay. Now is it correct? Otherwise, yes. Now your bulb is here. The batteries are here.
Madam, excuse me, madam.
Okay, sorry about that. I just dropped this call. Okay, so did you understand the logic behind, the O gate? Okay, it should be like this. Okay, so if either one of these switches are closed, I mean, if one is open, you can light the bulb. Okay, can you hear me?
Yes, madam.
Okay, right. So this is the logic behind the OR gate. That previous one I drew was not correct. Okay, so you identified that, so it's good. Okay, right. Then let's go to the next one. Okay, so the truth table is like this. So if you get two zeros, the output is 0. So if you get 1 for either of these inputs, so you get 1 as the output. This is the OR gate truth table. Now, if we are looking at the NOT gate, the last gate, now example is now we can understand by lighting the street lamps automatically, right? So when the sunlight is there, the street lamps are off, right? They are not switched on, right? If the sunlight is not there, the street lamps will be switched on, right? That is the logic of the NOT gate. So if the signal is there, then it means it is, I mean, now the sunlight is there, the lights are not switched on, okay, not switched on. But if the sunlight is there, so if the signal is there, if the sunlight is not there, sorry, if the sunlight is not there, the street lamps will switch on. Okay, so this is the opposite side, right? Of if the sunlight is available, the electric lamp is off. So if the sunlight is unavailable, the electric lamp is on. This is an example for the NOT gate, right? So if we take availability of sunlight as 1, then the electric lamp is off, mean that is 0. We will denote it as 0. When the sunlight is not there, then it will switch on. That means 1, right? So if we take this, so the output of the NOT gate is the opposite of the input. So if you get the input as 1, you get the output as 0. So if you get input as 0, you get the output as 1. It's the opposite of its input. Okay, it's the opposite of the input. Now this is the symbol of the NOT gate, right? This is the symbol of the NOT gate. So if we input A, you denote it by A bar. The output is A bar. Okay, if you input A, the output will be A bar. So if your input is 1, what is your output? If your input is 1, what is your output?
1 bar.
0.
0, yes, that is 0. Okay, 0. So if your input is 0, what is your output?
1.
1, yes, it gives the opposite of your input. It's very easy. The truth table of the NOT gate is like this. If it is 1, if the input is 1, you get 0. If the input is 0, you get 1. Now, that is it for your about the gates. Okay, then we have to take down this note. Okay, shall we then? Right. Let's take down this note.